Hello everyone, I am Ashwin, a PhD student at Georgia Tech, and today I am presenting our work on mixed RRAM and SRAM SoC with in-memory and near-memory based computing for target tracking. Before we begin, I would like to thank TSMC for the technology and chip fabrication support. This is the agenda of today's talk. I'll talk about the frame and event-based vision and the complementary advantages of using them, and then talk about the hybrid tracking algorithm that we built it. Followed by that, I'll talk about the heterogeneous accelerator SoC that we have built for compute in memory and compute near memory. Present some measurement results before concluding. Let's start with event and frame-based vision. Frame-based cameras provide synchronous image frames, as shown here. They capture detailed spatial information like color and texture. Convolutional neural networks are typically used to process this data with high accuracy. However, because of large sizes of CNN models and limited frame rates of frame-based cameras, the speed of processing remains limited. So therefore, with frame-based cameras, high accuracy tasks are possible, but high-speed tasks get limited. A high-speed alternative to this are recently popularized event cameras, which are shown here. These cameras capture change in intensity of a pixel instead of the absolute intensity. This video shows a rotating disk with a dot on it. The standard frame-based cameras capture discrete image frames. The event-based cameras, on the other hand, capture asynchronous stream of events when the intensity of a pixel changes. As there is no redundant information about the stationary background, detailed temporal information can be packed on the bus. Spiking neural networks process this asynchronous data streams with high speed of processing. But because of the noise in event generation and unreliability of training of spiking neural networks, the accuracy of event-based processing remains limited. Therefore, the two modes of sensing provide a trade-off between accuracy and latency. One task where a set of tasks for robotic vision require both high speed and high accuracy simultaneously. One such task is target identification and tracking. A camera is mounted on a predator drone and it needs to identify a target accurately and then follow it with high speed. This image shows an image captured by the predator drone with a target prey annotated with a bounding box. This task is typically carried out using object detection with convolutional neural networks. This is because of the high accuracy of object detection that CNN models have demonstrated. But because of large models and limited compute that we have on drone platforms, the speed of processing with such frame-based processing remains limited. Biologically, this task is similar to predation in natural environments by predatory animals. The animal needs to identify its prey accurately and then track it with high speed to not let it escape the field of view. Biology uses multiple sensors like vision and inertial sensors together, and multiple subtasks like object detection and self-motion cancellation are carried out in parallel. Their outputs are fused to identify the target prey and actuate motion to intercept it. We take inspiration from this multi-sensor fusion to use event and frame-based processing together. Convolutional neural networks match the sensing modality of frame-based cameras, and asynchronous event stream from event cameras match the processing modality of spiking neural networks. Similar to their sensing counterparts, SNNs and CNNs also show a trade-off between accuracy and latency. CNNs reach high levels of accuracy because of the detailed spatial features that they extract and reliable training methods that are there for CNN training. On the other hand, spiking neural networks process with really high speed because of sparse event-based processing, but their accuracy remains limited because of the noise in event stream that event cameras give, and also unreliability of training with event-based processing. So to mitigate this trade-off and reach high accuracy and high speed simultaneously, we proposed a hybrid event and frame-based target tracking algorithm. So our algorithm uses a frame-based pipeline, which uses a frame-based camera and a convolutional neural network for object detection, which is shown here. This gives out accurate but low speed outputs that are shown in this video. So you can see the reliability of outputs is large, but the throughput is low. This video is captured using a simulator that we built. This allows us to instantiate and control multiple drones within virtual environments and carry out experiments like this. Here, the images captured are from the perspective of a predator drone, and the prey drone that you see in this video is flying independently. To compensate for the low speed of processing that this frame-based pipeline has, we added an event-based pipeline in parallel to it. It has an event camera and a spiking neural network, where the spiking neural network carries out self-motion cancellation. It basically filters out the activity generated by the stationary background as the predator drone moves. This video shows how the outputs look like. So it has a high throughput output, but the accuracy remains limited and there are a lot of noisy outputs. This is because of the noise and event stream that you see in this video, and also the shallow network that we use for high speed of outputs. A fusion algorithm uses these two outputs together to improve the overall throughput of the system without letting the accuracy go down. For this, it runs the event-based pipeline continuously and periodically triggers the frame-based pipeline for a reliable output. A CNN output is used as an anchor to check if the incoming SNN outputs are spatiotemporally consistent or not. If they are consistent, they are used. If a SNN noisy output comes out, then it is filtered out. In this video, you can see yellow boxes corresponding to SNN outputs and blue anchors given by the CNN outputs. This increases the overall throughput of the system without letting the accuracy go down and allows us to go with higher throughput of processing that we need for these kind of tasks. This work was published recently, and we showed multiple evasive trajectories in multiple virtual environments and also some experiments with real drones. Interested audience can take a look at this details of the algorithm. So the novel part of processing is the self-motion cancelling SNM. As the predator drone moves, even the stationary objects that are present in the background create events, and to filter that activity out to keep only the target generated activity, the self-motion cancelling SNM is added. So this shows as the predator moves, a lot of trees in the background also create events, and in addition to the target prey which is moving. Intuitively, if the speed of self-motion is higher, there are going to be more events that get generated. So similar to predatory animals, we take inertial inputs about the self-velocity of the predator to cancel the activity corresponding to the self-motion generation. So as activity is proportional to the speed of self-motion, the cancellation also needs to be proportional to it, and these inhibitory synapses do that. In addition to that, if a background stationary object is close, the events that it is going to generate are more. So the cancellation is also proportional to the depth of the stationary object from the predator. After cancellation, we do cancellation in both horizontal and vertical directions using layer 2H and 2E by taking the horizontal and vertical components of self-velocity. And the activity that is filtered out is fused in layer 3. It can be seen in this video. Yeah. So now we have a higher throughput of processing with accuracy conservation. How does it help us? So in this video, we show a trajectory of a predator drone where it is trying to escape the field of view of the predator, and the CNN only processing tracks it for a while but then loses track of it because of low throughput. Now instead of that, if we repeat the same trajectory with fused system using both SNN and CNN together, this is how it looks like. So the yellow outputs are from the event-based processing, and periodic blue anchors can also be seen. This gives us a higher throughput of processing and tracking continues for a longer time. So with this, we are able to track for longer periods of time. Now to build an edge SoC with these two pipelines, we first analyze the compute requirements of them. The CNN uses well-known multiply and accumulate operations shown here, and compute in memory with resistive devices is one mode of processing that has shown high efficiency previously. Basically, the resistive devices are programmed in high and low resistance state, and the activations X are applied at the word lines as shown. If the applied activation is 1 and the resistance is in low resistance state, then a current flows through and gets summed over the bit line for multiple word lines. So the bitwise multiplication happens within a cell and accumulation happens over a bit line. The current is read out by an ADC which is sitting at the bottom of the bit line to convert it back to digital output. The SNN has a different requirement because spiking neurons operate with integrate and fire dynamics. If an event is generated at x, y, then the membrane potential of the neuron at x, y needs to be updated like this. If the membrane potential exceeds the threshold, the neuron generates a spike, and this triggers activity in the layers that follow. A medium-sized event camera generates more than 10 million outputs per second, and this causes large number of memory accesses to support that operation in real time. For this, for this to support that high bandwidth memory, we have compute near memory where we have small banks of SRAM distributed throughout the compute and small compute to carry out the integrate and fire dynamics near it. So compute in memory suits CNN operation, whereas compute near memory suits spiking neural net. Now, if this SoC is to be mounted on a predator drone, we have to address a set of constraints. First is energy availability, and consequentially the compute is also limited. The first constraint is that we need to process everything with low energy in spite of the large number of MAC operations that CNN needs to process. For this, we used our experience with computing memory with RRAMs from our previous tapeouts, and we know that non-volatility of RRAMs preserves the stored data even if we isolate it from power source. Now for this application, we have CNN which gets sporadically triggered, and power gating really helps us as it allows us to save almost 95% of the power. The other requirement is high speed of processing for the large number of events that are going to get generated with event camera. And this requires multiple sequential memory accesses. For this, we distributed the compute in a compute near memory blocks, which can support more than 11 million events per second. And finally, the computation accuracy for CNN needs to be high because CNN anchors are going to decide the overall accuracy of the system in the end. So reliable computation is needed for CNN, and compute in memory is known to have variation-induced accuracy degradation. To prevent the accuracy degradation, we add triple error correction module within every RRAM module, and this limits the application level accuracy to less than 1%. So with these three features, we are able to satisfy the power, performance, and accuracy constraints simultaneously. And we built this heterogeneous SoC for which the architectural features are what now I'll show. So Cortex M3 communicates with the external world and accelerators on chip. The computing memory implements CNN and compute near memory implements SNN. There are 32 modules or processing elements for implementing computing memory and 24 processing elements for mapping SNN with compute near memory. Let's first look at how the SNN is mapped on compute near memory. This is the network that is carrying out self-motion cancellation. For every generated event, layer 2H and 2V need to be accessed to cancel out the activity. For this, we need to have multiple small banks of SRAM to operate. We divide the input frame into multiple small windows as shown here, and each window is mapped on one of the 24 processing elements. The incoming events are buffered, decoded, and fed to the processing element to which it corresponds to, depending upon which window it is from. A processing element is shown inside the blue boundary. The small banks of SRAM implement layer 2H and 2V as shown. And similarly, layer 3 is also implemented in small banks. The accumulation and spiking operation is checked with a small comparator near the memory, and the spikes in layer 2H and 2V cause spiking in layer 3V. The output spikes are also buffered for the cortex to read and infer the position of the target. This distributed processing allows us to reach more than 11 million events per second for real-time processing with DVH data that I'll show later. So CNN is implemented using computing memory, and that computing memory is implemented using RRAM macros. So each of the 32 processing elements or modules have 5 RRAM macros within it. Each macro consists of 256 cross 256 1T 1R crossbar array as shown here, with 16 lanes of ADCs capable of reading it out in parallel. One of the 5 RRAM macros can be used for computing memory or error correction, depending upon the expected variation. Both module and macro can be isolated from the power source if not being used, and the non-volatility preserves the stored data. An interesting feature of the chip is that user can dynamically select how many word lines to use. So if the user starts with 128 word lines, this allows 4 times more throughput compared to using only 32 word lines. But with using large number of word lines, there are chances of ADC overflow and erroneous computation with variations. So the user can start with 128 word lines for higher throughput. If an ADC overflow is observed, then the user has option to either continue with erroneous computation or revert back to lower number of word lines to trade off the speed for accuracy. Another well-known challenge in computing memory with resistive RAM devices is variation-induced accuracy degradation. The resistance of each device has a variation, and therefore the current on the bit line tends to have a distribution like this. As more and more devices start passing current, the distribution starts getting wider, and sometimes it leaks out in the neighboring region, causing ADC misread. So this confusion matrix shows expected and measured ADC output, and when a large number of devices are conducting, you can see how the ADC is misreading outputs. This is because the voltage at the terminal of the ADC leaks out in the neighboring region. The bit error rate that we measure because of this is of the order of 10 raised to minus 3, whereas to compare with SRAM has a bit error rate of 10 raised to minus 50. This corrupts the accuracy of the overall system if not corrected. So to correct for this, we add triple error correction module within every processing element, and it was published recently. This basically has a set of control bits in addition to compute bits. Control bits are like parity. For every read operation, the outputs of the control and compute bits are compared to check if there is a discrepancy. If a discrepancy is observed, less number of word lines are read out. And if the discrepancy continues, the number of word lines are reduced even further. So the sequential processing for error reduction causes a latency overhead, but corrects for the errors. So we built this chip with these features, and now I'll present some measurement results. This is the die shot where we have Cortex M3 sitting at the center and communicating with the computing memory and compute near memory modules. We basically need multiple voltage levels to support RRAM set reset operations, and that was built, that they were built using a voltage regulator on the test PCB. We have an external MCU that communicates the user commands to the accelerators on the test chip through the ARM Cortex. The chip can be programmed using Python commands as shown in the demonstration yesterday. The first feature of the chip is 2 levels of power gating, where both module and macro can be independently isolated from power source. The passive power consumed by the macro and module show a tight distribution. Now if we turn on multiple macros sequentially, this is how the power varies. So basically we turn on a module and turn on all the 5 macros within it sequentially. As more and more number of macros start operating, the power increases linearly. What this means is if we have a layer of CNN mapped only on 5 macros, then instead of burning 100 milliwatts corresponding to operating all 120 macros simultaneously, we can just switch them off and use the 5 macros to save power. The peak active power consumed by different blocks are shown in this figure. The majority of the power is consumed by CNN computing memory, and this shows why power gating is really helpful to bringing the power consumption down. This shows the efficiency of the chip, where the total efficiency can reach up to 73.53 TOPS per watt and 90 megahertz. This chip also shows highest computing memory throughput because all modules, word lines, and macros are capable of operating in parallel. We also characterize the event pipeline for SNN as shown here, and with 100 megahertz clock, the SNN can process more than 11 million events per second as shown. So now we have all the pieces of the puzzle in place. This is how this chip benefits the application. SNN provides high-speed outputs that are shown here, and they are compared with the most recent CNN anchor to check if they are correct or not. If there are multiple incorrect outputs, the suspicion level rises as shown here. If it hits a threshold, it basically means that we may not be tracking the correct object and a new CNN anchor is necessary. So the CNN is triggered for validation, and this causes the CNN to run and provide us with an accurate output. This CNN output or anchor is used for the SNN outputs to check the correctness of SNN outputs that fall. So if you look at the power trace of running this, before the CNN gets triggered, the compute-in memory block consumes really low power. Once the CNN gets triggered, the macro that stores a particular layer is turned on and the power trace varies depending upon how many macros are storing a particular convolutional layer. This is for MobileNet YOLO object detector. The average power consumed when the CNN is running versus when the CNN is off shows around 92% power saving. So this kind of power gating is really helpful if we have applications where the computing memory needs to be sporadically triggered. So coming back to the problem of variation-induced degradation, the raw bit error rate of 7 into 10 raised to minus 3 causes a massive 40% reduction in accuracy for MobileNet YOLO. Single error correction is not enough to suppress this bit error rate. Double error correction suppresses the bit error rate by 2 orders of magnitude and keeps the accuracy degradation to less than 1%. Triple error correction can be used if the bit error rate is even worse, as it might with the retention problems in RRAM. And finally, this is the system level trade-off that we started with. CNN has higher accuracy but is slow to process, and SNN is fast to process but has a lower accuracy. By using them together in the hybrid manner, we could get both high speed and high accuracy simultaneously, while also reducing the processing power. To compare it with the previous works, we use both SRAM and RRAM based compute to accelerate CNN and SNN simultaneously for target tracking application. The bit error rate is reduced by embedding triple error correction modules within computing memory. We use point-to-point communication for SNNs to make it work with high speed to process the data from event camera in real time. And finally, with our power gating, we can keep the average power low, and the computing memory achieves maximum throughput achieved so far in literature by using all the modules in parallel. To summarize, we started with a fundamental trade-off in frame-based vision to process a collaborative algorithm to mitigate it. We identified the processing requirements for each pipeline and mapped the CNN on compute-in memory and SNN on compute-near memory. This chip of heterogeneous accelerators showed performance in both power accuracy as well as latency. To conclude, hybrid vision is beneficial and mitigates accuracy versus latency trade-off. We use both RRAM and SRAM based accelerators for accelerating SNNs and CNNs. By using power gating, error correction, and parallel operation, we could get both high-speed accuracy and power requirements simultaneously. And we believe that exploration in such heterogeneous cross-layer design can help us mitigate fundamental limitations in sensing and processing. So these are the key references, and thank you very much for your time and attention.